Hi, this is Eduardo Sanchez from the University of Guanajuato in Mexico, and I'm gonna present you improvements in methyl ketone production through intensified processes. Recently, methyl ketone, or MEK, has been screened as a possible biofuel. Currently, MEK production is generated as an oil-derived good. An interesting process to produce MEK is using 2,3-butanediol or 2,3-BD. Once 2,3-BD is produced, it can be dehydrated and converted directly to MEK. Song et al. Has reported a set of detailed equation and reaction kinetics for the dehydration of 2,3-BD to MEK over a catalyst of calcium phosphate. In subsequent work, Song et al. Presented an alternative to produce and purify MEK from 2,3-BD. So, the aim of this work is to propose intensified alternatives based on intensified schemes such as reactive distillation and extractive distillation to produce and purify MEK. The conventional process previously presented by Song et al. Is presented in the point number 2. You can see this conventional process consists of a reactor and a set of a lot of unit processes. Song et al. Consider the kinetic model presented in point number 3. This kinetic model considers all the chemical reaction, the activation energy, and the kinetic constant. Using this kinetic model and using Aspen Plus, we could design two intensified alternatives. Both alternatives consist of a reactive distillation column followed by an extractive distillation column and a set of 3 conventional distillation columns. Scheme A and Scheme B are practically the same. The only difference is in the location of the conventional distillation columns. In order to evaluate both alternatives, we consider 3 indexes: 1. Their boiler duty, 2. The echo indicator 99, and 3. The CO2 emissions. Once both alternatives were modeled and designed, we conclude that alternative A was the best, and here in the results you can find a table with the design parameters and the general results of both alternatives. Once the intensified alternative was designed, and through a sensitivity analysis, a minimal energy scheme was obtained with a conversion of 99.86% and a selectivity of 44%. The energy consumption of the intensified scheme was 5073 megajoules per hour, and in the hypothetical scenario where all MEK produced was burned, the energy profit would be 8601 megajoules. As conclusion, we could say that in this work, an intensified alternative to produce MEK from 2,3-BD is proposed using calcium phosphate as catalyst. After evaluation, the direct scheme, Scheme A, resulted as the most promising one, with energy requirements of 11.6 megajoules per kilogram of MEK. Regarding the environmental impact, the direct scheme reported 7.07 tons of CO2 per hour of greenhouse gas emissions. Thank you.